our guest speaker for this first virtual lecture, Professor Dr. Farzad Kobarfad. Professor Farzad is a professor of medicinal and pharmaceutical chemistry from School of Pharmacy, Shaheed Beheshti University of Medical Sciences, Tehran and Iran. On behalf of Comstech, I would like to thank Professor Dr. Farzad for giving us his valuable time and sharing his research experience with us. And with this, I would request His Excellency, Professor Dr. Iqbal Chaudhry, Coordinator General Comstech and Director ICCBS, to welcome our guest speaker today. Over to you, sir.
Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuhu. Good morning, good afternoon, and good evening, ladies and gentlemen, all the participants from different regions of the world. This is a new series of lectures and presentations, which is called Comstech Innovation Laboratories. And the concept of innovation laboratories are largely to introduce not only the basic fundamental concept, but also the practical application of some important aspect of the application of science and technology. And what can be a better start than talking about a very important problem and the technology which is available to detect that. And this is these large number of metabolic disorders which need to be detected in newborns or neonatals. For that, lots of technologies have been developed, but the one which has now become almost a standard technology is mass spectrometry. And mass spectrometry has turned out to be a very important tool, which used to be a research tool. It is now in diagnostic laboratory. And this innovation laboratory is all about understanding the concept of use of mass spectrometry in detection of hundreds of these metabolic disorders, which are largely genetic disorders or congenital disorders of different kinds, which babies inherit from their parents. And their detection always on time is very, very important. And the speaker which we have invited for this innovation laboratory, who would give you the concept and a tour of his lab, is actually a practitioner of this science. He has established a very good laboratory in Tehran, in Shaheed Beheshti Medical University, which is part of Comstech Consortium of Excellence. And we have had the honor of working with Shaheed Beheshti Medical University through my very dear friend, Professor Dr. Abdul Majid Ayatullahi. And of course, I now met with Professor Dr. Zali, the Vice Chancellor of this wonderful institution, a very prestigious medical university. And this university is responsible of taking care of health of large number of people, and this laboratory playing extremely important role. So during my last visit to Professor Farzad laboratory, I was impressed and fascinated from the efficiency through which they do thousands of samples. Farzad, of course, is very well known to me since several decades. I have seen him evolving into a very prominent scientist from a young scholar, and I'm very, very honored to have him for this first innovation laboratory. I would like to welcome you to this new series. I hope you would be able to benefit from this new concept of introducing both the theory as well as the applied sciences, the appliances which are actually used, the instruments which are deployed for different works. And this is the most important series which we consider important for everyone for understanding of science and its application. With this, I would like to thank you all for participation in this series, and thank you, Khadima, for arranging it. And now my colleague would actually introduce Dr. Farzad.
Thank you very much, sir. With this, now I would request Professor Dr. Musharraf to introduce our guest speaker today.
Assalamu alaikum, everyone, and assalamu alaikum, Brother Farzad. How are you?
Assalamu alaikum. Thank you so very much indeed. It's a pleasure to be with you, and thank you for organizing the event.
Indeed. Indeed, my pleasure as well to introduce you. Dr. Farzad actually did his PhD in medicinal chemistry from University of Philadelphia, USA, and he's currently working as an associate professor at the Department of Medicinal Chemistry at Shaheed Beheshti School of Pharmacy, Tehran. He has 5 books and 2 patents and several research articles to his credit. In addition to that, he's also serving as a technical coordinator of Iran Doping Control Laboratory, Tehran, as a member of editorial board of so many prestigious journal, including Iranian Journal of Pharmaceutical Research. So with this brief introduction, I would request Brother Farzad to please continue his lecture. Over to you, Brother Farzad.
Well, thank you for the nice introduction. And I would like to say Assalamu alaikum to all the participants. And I would like to thank all the organizers of this event. My special thanks goes to Dr. Iqbal and Dr. Khazima for making this event to happen. We had the pleasure to have Dr. Iqbal, the prominent scientist known all over the world in our center, Phytochemistry Research Center, when he was receiving the very prestigious award of Mustafa this year. And during his visit from our lab, we talked about the neonatal screening metabolic disorders, and he was kind enough to invite me to give you the lecture regarding this technique, and I'm very happy to be with you today. With that, I would like to start by talking about a little bit about the metabolic disorders, and then I would go to the technical aspects of this test, and then after we are done with the talk, we are going to go to the lab and we will have a demonstration of the practical aspect of this technique. Thank you so much. But the only problem that we have is that we don't have the control of the slides. So I have to ask Dr. Khazima to work with me to change the slides. So these are the outline of my talk. I'm going to talk a little bit about the inborn errors of metabolism, which are called IEMs. These are those the metabolic disorders which are congenitally transferred to the babies, and they have to be monitored. And I'm going to talk a little bit about the importance of these diseases and the importance of the diagnosis on time. We will have a look at the biomarkers of inborn error of metabolism. And then I'm going to talk a little bit about the capacities of the mass spectrometry to be used for the purpose of diagnosis of these type of metabolic disorders. And then we will have the practical aspect of this
Khazima, we cannot hear you. Hello.
Yes, Dr. Musharraf, I'm calling him. I can also not see him, hear him.
So there is a problem from his side, actually. Disconnect, I think. Be connected soon. Fazima, I think Dr. Farzad is connected, but I think its volume is not properly connected.
Yes, Dr. Musharraf, he is in the meeting, but we cannot hear him. So I was just calling him, and let's see if we can do it.
Do you have my voice now?
Yes,
Yes.
Dr. Farzad, we can hear you.
Okay. Sorry about the technical problem. So if we have
Yes,
the
please
next,
continue.
if we could have the next slide, please. Yeah, the point is that some babies are born with congenital metabolic disorders when they're born that could not be detected by physical examination because a baby when he or she is born is disabled, and if by physical examination, you will not be able to recognize if she or he has metabolic disorders. So, but there are some metabolic disorders which could happen congenitally, and then if they are ignored and if we miss them, the baby is going to go to the normal diet of mother's milk. And since she or he has not have the enzymes to metabolize some of the components of mother's milk, those components are going to accumulate in his blood or her blood, and they would cause some problems from kidney failure to liver failure, sometimes mental retardation, sometimes physical retardation, even sometimes the baby is going to die because of the metabolic disorder, just because she or he could not metabolize mother's milk, some of the components of the mother's milk. For instance, phenylalanine is one of them. And I think everybody knows about phenylketonuria, which is one of the very famous, maybe the most famous metabolic disorder. And in this disorder, the baby is not able to metabolize phenylalanine, which is one of the components of the proteins of the milk, mother's milk. And if the baby is fed by a mother's milk and he or she doesn't have the enzyme, then we will have an elevation of the concentration of phenylalanine in the blood. And that would cause some problems such as mental retardation and other consequences. Could we have the next slide, please? Yeah, these are some of the metabolic disorders that are famous. And as I said, PKU is one of them. Maple syrup is another one. And the other one is medium chain fatty acid the enzyme deficiency, which is called MCAD. And these are the famous metabolic disorders which would lead to the failure of, for instance, kidney, liver, sometimes mental retardation, and as I said, MSUD may cause sometimes death, and baby is going to die because of the disorder. And the point is that the consequences and the damages which are caused by these metabolic disorders, when they happen, they are irreversible and we cannot take them back. And the baby is going to have the disorder in his or her life. And it will finally cause a very serious problem for the baby himself or herself and the family and the parents. And it is basically a disaster when a baby is having a congenital metabolic disorder and it is undiagnosed. But the good news is that if we recognize and if we diagnose the metabolic disorder on time, then we could have treatment measures, and we could do something about it. And if we, for instance, change the diet for the baby, and she or he is fed by a special type of milk, we could manage and we could handle the disease, and the baby is going to be saved this time, this way. And he or she will not go for mental retardation, irreversible physiological disorders such as kidney failure and liver failure. So the point is that these consequences and these damages are the type of damages that we would never want to have on any babies. And if they are diagnosed on time, they are manageable, and we could handle them and we could treat them. So the only point is that we have to have a system by which we could diagnose the diseases on time and very fast. When I say on time and very fast, I mean the first 10 days of the baby's life. If we could diagnose the diseases during the first 10 days of the baby's life, then we will be able to handle this, and we could treat the baby. If it goes longer and the baby is on the mother's milk diet, and we miss the diagnosis, then we should expect for the very disastrous consequences of these metabolic disorders. Could we have the next slide, please? Yeah, this is a statistic about the prevalence of metabolic disorders that for a few countries, for instance, United States and Germany. And if I want to give you an average number of the prevalence of these type of metabolic disorders, it is 1 to 4,000 babies. That means from 4,000 babies which are born all around the world, one of them is born by one of the metabolic disorders such as PKU, MSUD, MCAD, MCHAD. There are many of them, and actually there are around 55 disorders which could be diagnosed, and they are treatable. And if we diagnose them on time and at the very beginning of the baby's life, then we could handle them, and we could prevent the damages which are caused by the metabolic disorder. So 1 in 4,000 is a big number. If you consider the number of the babies which are born every day all around the world. So this is the importance of diagnosis of inborn error of metabolism in the babies. Next slide, please. Yeah, the purpose of metabolic disorder screening is diagnosing the metabolic disorder on time to prevent the irreversible damages which is occurred by the metabolic disorder. And we could have the effective treatment after that. So what we are looking for is a screening system by which we could diagnose the metabolic disorders during the first 10 days or first month of the birth, and then take the proper actions to treat these diseases. So this is the whole purpose of this system, which, as you may all realize, it's a very important and very crucial mission. Next slide, please. Well, if I want to give you a history of screening, it goes back to the 60s when an American physician named Robert Guthrie for the first time invented a screening test for PKU or phenylketonuria. As I said, phenylketonuria is a disease in which the baby doesn't have the enzyme to metabolize phenylalanine, and the phenylalanine is going to go up in the blood, and we will have the consequences of mental retardation and so on. So Guthrie invented a test by which the phenylketonuria could be diagnosed. But the test that he invented was based on the microbiological aspects, principles. And actually, he was a microbiologist. And he invented a test based on the Bacillus subtilis. And he was able to diagnose the PKU. But that was one of the metabolic disorders. And as I said, there are over 50 metabolic disorders which could not be recognized just by the microbiological test that Guthrie invented. So historically, Guthrie is the inventor of the screening process. And what he did was still going on. And the thing is that the test should be easy to run. The sampling should be easy because we want to do it for all the babies which are born. And the samples should be transferred to the lab very easily. So Guthrie, in order to do this, what Guthrie did was inventing a system in which you get a drop of blood from the baby's heel, and you put it on the filter paper, a special type of filter paper, and then you dry it. And the dry blood spot is sent to the lab. And when the lab receives filter paper, they will start the process of screening, and they could diagnose the disease. So the Guthrie card, the filter paper, which is used in this process, is called Guthrie card in honor of Dr. Robert Guthrie for his effort to set up the test of screening. But as I said, the screening, which is invented by Guthrie, is good just for one metabolic disorder, and it misses all the other metabolic disorders. And it was just like this until the mass spectrometry came into practice, and mass spectrometry was used in clinical chemistry. And after that, which started from 90s, we are able to diagnose over 50 metabolic disorders in very fast pace, and we will be able to diagnose all of them at once and together. Next slide, please. Yeah, as I said, mass spectrometry has the capability of diagnosing and detecting all the biomarkers which are related to the metabolic disorder, over 50 metabolic disorders. Each metabolic disorder has its own biomarker, and the related biomarker should be monitored by a system. And as I said, it is very crucial that the test is done very fast. And considering the number of the newborn that every day are born, so we are talking about many samples a day. And on the other hand, if you want to screen for 50 disorders, we will have over 50 biomarkers which should be monitored and measured. And based on the concentration of each biomarker, we could say that there is a disorder or there is not a disorder. So as you can realize, the test has to be fast, it has to be accurate, and it has to be comprehensive. That means we need to have all the biomarkers measured and monitored at the same time. Could we have the next slide? Yeah, the biomarkers which are measured in metabolic disorder screening are divided and classified in two groups: amino acids and acylcarnitines. Next slide. We all know amino acids, and we all know about the role of amino acids in metabolic processes of the body. And each amino acid has its own route of metabolism, and there are many enzymes involved in the metabolism of amino acids. And if we have a defect, or we don't have the enzyme for the metabolism of amino acid, then we will have the accumulation of the amino acid, and then we will have problem with that. Next slide. The second class of the biomarkers which are measured in metabolic disorders are acylcarnitine. Carnitine is the shuttle for fatty acid to be transferred to the mitochondria, as everybody knows. And when we are talking about the metabolism of fatty acids, carnitine has a crucial role to take the fatty acid and transfer them to the mitochondria for beta oxidation process. And then we will have energy out of fatty acids. But if this shuttle is defective, if carnitine could not transfer the fatty acid to the mitochondria, then beta oxidation is disturbed and it is interrupted. And then we will have different type of disorders because of that. Carnitine gets the fatty acid. It has a hydroxyl group in its structure, which could be linked to the fatty acids, and then fatty acid is transferred to the mitochondria. And different fatty acids have different roles in the metabolic processes of the body. We could have acetyl as the 2-carbon fatty acid. We could have propionyl as a 3-carbon fatty acid, and so on. It goes up to C18 fatty acid, which has 18 carbon. And as you see in this picture, carnitine is the one that is connected to each one of these acyl groups. It could be 2, 4, 5, 8, 16, 18, and so on. And this is what carnitine does. It takes the fatty acids and it takes it to transfer them to the mitochondria. And if, in all of these processes, there are enzymes involved. And if we have the enzymes which are not working good, then we will have the accumulation of that fatty acid, and the accumulation of fatty acid in the blood is going to cause metabolic disorders. Next slide, please. So what we need is a screening system by which we could diagnose the metabolic disorders, either if they are for amino acid or for acylcarnitine. But what we need to run the test is 3 conditions. And actually, we need 3 criteria for the test. The test has to be fast. Because as I said, if we miss the first days of the birth, the first 10 days of the baby's life, then we should expect the consequences. We want to diagnose the diseases at the very beginning of the life. And if there is a disease, we want to take the baby off the mother's milk diet and put him or her on a special diet. So it has to be fast. Otherwise, I mean, we have missed the baby, we have missed the pathological condition, and we should expect the consequences. The other point is that the test has to be very accurate, because if you misinterpret, or if you kind of do the test wrong, then there would be very disastrous consequences. For instance, if you diagnose a baby as a healthy baby, and the disorder is missed, so we have to expect the consequences and the damages, which, as I said, are irreversible. On the other hand, if you diagnose a baby, a positive case, if you diagnose the baby positive and he or she is not defective and the baby is not having the metabolic disorder, then the parent would be panic. And just imagine that you have your baby and the lab tells you that your baby has a metabolic disorder. What would be your feeling, and what would be the consequences for the parents? So you don't want to give the wrong number, wrong result of the test. You don't want false positive. You don't want false negative. So the test has to be very accurate. Otherwise, there would be consequences. Either you have a false positive or false negative result. And the other point is that, as I said, there are many biomarkers, and there are many metabolic disorders, over 50 of them, that has to be monitored at the same time and together. You cannot do the test and for each biomarker one by one. Because if you spend time just for one biomarker and then you go for the second biomarker and for the third biomarker, and you have to go over 50, and that would take many hours to get the results. And considering the a large number of the samples that you have to analyze each day, you cannot do it. You cannot monitor all the biomarker one by one. You have to monitor, you have to set up a test by which you can monitor all the biomarkers together accurately and very fast. This is the characteristics of the test that we have to have if you want to have a screening, an efficient screening process. Next slide, please. The instrument and the technique which has this characteristic is tandem mass spectrometry. And before that, before the tandem mass spectrometry is invented and come to the practice in clinical chemistry, we were not able to diagnose all the metabolic disorders together. But with tandem mass spectrometry in hand, we could have a test which takes 2 minutes, only 2 minutes, to run the samples and have all the samples analyzed and get a very decisive result. Mass spectrometry is very selective in monitoring the biomarkers, and I explain it later. And having that accuracy, we could be sure that the diagnoses are accurate, and we will not have any problem with the misdiagnosis of the metabolic disorders. And yes, mass spectrometry is comprehensive. I'll explain it later in my slides, but one of the very strong capacities and capabilities of mass spectrometry is the ability of the technique to simultaneously monitor and measure all the biomarkers together and separate them from each other without being them mixed up. So this is one of the characteristics of mass spectrometry that are used, and mass spectrometry satisfies all the 3 criteria that I mentioned. It is fast, it is accurate, and it is comprehensive. Next slide, please. If I want to explain a little bit about the mass spectrometry, I would always compare mass spectrometry with what we do in archaeology. You know, in archaeology, we get the fragments and we get the parts of an skeleton like dinosaurs, and we put them together based on the anatomy, and we come up with a structure, a whole structure, which we call it a dinosaur. No one has seen the dinosaurs, and we all believe that they existed. Why? Because we have the evidences. What are those evidences? They are the fragments of the skeleton of the dinosaur, which have been put together based on the anatomy. And we all believe that the dinosaurs lived once, although we have not seen them, and they have been here for million years years ago. So if we compare this with mass spectrometry, when we have a structure of a compound like this, if we fragment the molecule in a certain and controlled condition of fragmentation, we always get parts and fragments from the molecule. And if we record them, these fragments, and we measure them, we come up with a mass spectrum. The mass spectrum is very repeatable. And if we keep the fragmentation processes constant, we could be sure that we always get the same pattern. And actually, mass spectrum is like a fingerprint for a compound. Even a small difference in the structure of two compounds would affect the pattern of the mass spectrum, and we will be able to diagnose, we will be able to prove the structure of the chemical based on the fragments that are formed during the mass spectrometry and the fragmentation process. Could we have the next slide? Yeah, in mass spectrometry, there are different methods of ion monitoring. Let me tell you that if we want to see a compound or monitor a compound by mass spectrometry, the compound has to be ionized. We have to change the compound to the ionized form, and then the mass spectrometer would be able to separate the fragments from each other, and the fragments are monitored by the mass spectrum, and the machine is going to record the fragments. And if we have those fragments recorded and we get the mass spectrum, then we will be able to have the fingerprint for the compound. And this is the way we usually determine the structure of a compound. But there is a certain type of ion monitoring which is doable and which is used in metabolic disorder screening, which is called SRM. SRM stands for selective reaction monitoring. What is selected reaction monitoring? What is a selected reaction monitoring? The selected reaction monitoring is a method of monitoring which is called the most selective monitoring system in mass spectrometry. I'm going to try to explain what happens during the selected reaction monitoring. What we are doing in selected reaction monitoring is monitoring the process of transformation of a structure to its fragments. For instance, if you have a compound like, can we have the next slide? Yeah, look at this structure. The compound has the molecular weight of 308. And based on the structure of the compound, when we take this compound to the fragmentation process in the mass spectrometer, it is able to lose a molecule of nitrogen, and it's gonna a nitrogen molecule is gonna go off the molecule, and the molecule is changed to a new fragment or new structure which has the molecular weight of 279. This process, transformation of the mother molecule to a daughter molecule, is monitored in mass spectrometer, and the process is called selected reaction monitoring. See, since the molecular weight of the mother molecule is 308, and after losing a nitrogen molecule, it's going to change to 279. This is the characteristic of this molecule. No other molecule has this characteristic. And this transformation, this transition from 308 to 279 is characteristic of this molecule. We use this specific type of transformation to monitor this compound. And even if we have other molecules together with this molecule, we will be able, I mean, the mass spectrum, the mass spectrometer is able to just monitor this process, and regardless of having other compounds, other molecules along with this molecule, the mass spectrometer will be able to just monitor this compound, and we could make the other compounds invisible, and we could avoid their interferences with this molecule. How is that done? Because if you adjust the mass spectrometer so that it just monitors the transition of 308 to 279, then even if you have other molecules with different molecular weights, they would be invisible to this monitoring. Since they don't have the parent molecule of 308, and when they are fragmented, they are changed to a compound which is not 279, they would not be monitored and they would not give signal in the mass spectrometer. How it's done, how this is done, how the selected reaction monitoring is done, I'm going to explain it into next slide. See, what we need in the mass spectrometer is something which is called triple quadruple mass analyzer. What is a triple quadruple mass analyzer? We don't have time to go in detail of this system, and I hope I could get a chance to explain this to you in a separate lecture, but for now, it is just enough to know that the system is consisted of 3 quadruples. The first quadruple is called Q1, the second quadruple is called Q2, and the third one is called Q3. And using these 3 quadruples in this arrangement, that Q2 is after Q1 and Q3 is after Q2, we will be able to do the selected reaction monitoring. How is that? So the mass spectrometer is capable of filtering the molecules based on their masses. What I'm trying to say is that if we have different molecules with different molecular weights, for instance, let's say we have molecular weights of 200, 250, 400, 500, and one of the molecular masses, one of the molecules that we have in our mixture has the molecular weight of 308, the compound that we just talked about. We could adjust the first quadruple, the Q1, so that it just let the molecule which has the molecular weight of 308 to pass through this quadruple. All the other masses which are different from 308 are filtered and they are eliminated and they are deleted from the mixture just by Q1, the first quadruple. This is something that mass does. It only let a certain molecular weight to pass through the quadruple. So let's say the Q1 is adjusted so that it could pass those molecules which have the molecular weight of 308, and it would filter and it would delete all the other masses. So as you see, this is like a separation system, separating all the molecules except for 308, those molecules which have the molecular weight of 308. So the 308 get to pass the quadruple one, the Q1, and it goes to Q2. The Q2 is called fragmentation cell or collision cell. In Q2, we have a process of fragmentation in different ways. I'm not going to go to the details, but in Q2, we get the fragmentation process. That means the compound which has passed through Q1 is delivered to Q2, and in Q2, we will have the fragmentation of this molecule. Based on the structure of the compound which has passed Q1, we will have different pattern of fragmentation. And the result is going to be specific fragments for the molecule which has passed through Q1. And based on the structure of the compound, they will give different fragments. Let's say we have the molecule that I showed you in the previous slide. And that molecule has the capacity and capability of losing a nitrogen molecule and change to the fragment which has a molecular weight of 279. If we have two compounds which are passed through Q1 together, one of them is compound A, the other one is compound B. Compound A is our target, the compound that I showed you in my previous slide. And compound B is a compound which is by accident having the same molecular weight as 308. And this is also passed through the Q1 and it has been delivered to the Q2. So we have two compounds delivered to Q2. One of them is our target, compound A, and the other one is another structure which is having the same molecular weight as the target A, and it has already passed, and they are both in Q2. We fragment them in Q2, but since they have different structures, they have different chemical structures. One of them is able to be changed to 279 by losing one molecule of nitrogen. The other one, since it has different structure with the compound A, the compound B is a different structure, it is not going to be able to lose nitrogen, and therefore it would give other fragments. Of course, it fragments, but it gives other fragments which are not equal to the fragment that we get from compound A. The compound A is the only compound which is able to lose nitrogen, and it would give the fragment which has the molecular weight of 279. Now, if we deliver all the fragments which are formed in Q2 to Q3, and if we adjust Q3 so that it only let the molecular weight of 279 at 279 to pass through it, then all the other fragments are filtered by Q3, and the only fragment which is allowed to pass through Q3 is 279. And now, if this whole system, Q1, Q2, and Q3 are adjusted like this, the way that I'm showing in this slide, the only compound which is allowed to pass through this system and give us a signal is compound A that I showed you in my previous slide. All the other compounds which have different molecular weights and different fragmentation patterns are eliminated and they are deleted from the process. And this way, the mass spectrometer is just monitoring our target without having any problem with the interferences of other compounds which are mixed with compound A. So this is how mass spectrometer is acting selectively to monitor a compound. Next slide, please. And the other very unique capability of mass spectrometer is that, as I said, you can adjust the mass spectrometer so that you can monitor the transition of a molecule to its fragment. But it is not like this, that we adjust the mass spectrometer as at a certain arrangement for the transition, and we cannot change it. The mass spectrometer is so fast that it could, for a couple of seconds, it could monitor the fragmentation of, for instance, 328 to 272 for a couple of milliseconds. The mass spectrometer is going to monitor for the first transition, which is 328 to 272. But mass spectrometer is so fast that it could jump into another transition, which is 295 to 188, which is characteristic for the second compound. And it could also jump into another transition and adjust itself so that it could monitor the transition of 421 to 290, which is another compound. You see, the mass spectrometer is capable of monitoring all these processes separate from each other and get the signal for each one of the compound without being disturbed with the transition of the other compound. So, you know, what it means is that we could monitor different reactions for different compounds together, and without having them mixed up. What I'm trying to get across by this slide is that mass spectrometer is able to monitor different ion transitions at the same time, and without getting them mixed up with each other, and generating a signal specific for each one of these compounds. That means the mass spectrometer is able to monitor all these three compounds separate from each other, but at the same time. And this is the highest capability of mass spectrometer, which could be used for metabolic disorder screening. As I told you, in metabolic disorder screening, we need a method by which we could monitor many biomarkers at the same time without having the biomarkers mixed up with each other, and getting a separate signal for each one of them, and then we decide based on the results. This is something which is called multiple reaction monitoring. That means we are monitoring different compounds and their conversion reaction to their daughter ions together. So this brings us to another terminology, which is called MRM. That means multiple reaction monitoring. And this is the most selective ion monitoring method and the most comprehensive ion monitoring method, which is used in metabolic disorder screening. Next slide, please. So let's go back to what we wanted to do. We have a drop of blood, which is placed on a filter paper. And of course, it has all the biomarkers in it. And beside the biomarkers that are our targets, there are other compounds and there are other components in the blood, in that dry blood spot. We would like to extract all the biomarkers that are targets from the dry blood spot. And then we would like to monitor them one by one and together, and without having interferences between them, and then get a signal which is converted to the concentration of that biomarker. So we have a few problems. The first one is extraction of the biomarkers from the dry blood spot. So we have to come up with a method by which we could separate and we could extract all the biomarkers, as I said, the amino acids and acylcarnitines. And we would like to extract them from the dry blood spot. And then we would like to inject them to the mass spectrometer and get a separate signal for each one of them. And the signals has to be representative of the concentration of each biomarker. So the first problem is the extraction problem, which is not a very difficult problem. It is just enough that we come up with a solvent which is able to extract all the amino acids and all the acylcarnitines together from a dry blood spot. Of course, other components will be transferred and will be extracted as well. But having the mass spectrometer, which is a very selective ion monitoring system, we are not worried about the other compounds which are extracted along with our targets, which are amino acids and acylcarnitine. Next slide, please. Yeah, the second problem, which is I would say, more difficult problem, is something which is called matrix effect in mass spectrometry. As I mentioned before, when we want to have a mass spectrum, if you want to have the mass spectrum of a compound, the compound has to be ionized. That means when we extract the samples from the blood, and we would like to monitor the sample by mass spectrometer, we have to adjust all the systems so that the compounds are extracted, and then when they are injected to the mass spectrometer, they have to be ionized. And if when they are ionized, then we will be able to monitor them and get a signal according to their concentration by the mass spectrometer. For instance, in this slide, as you see, first we have 4 nanogram of the target compound, but if you just inject this sample to the mass spectrometer, you get no signal because they are not ionized. So we have to come up with a system that ionizes the analytes, ionizes our target compound. And when they are ionized and they are injected to the LCMS system, then we'll get a signal which is proportional to the concentration of our target. But the point is that when we are talking about the blood, the dry blood spot being extracted by a proper solvent, beside our target compound, all other components of the blood is also extracted to the solvent, and they are mixed together. And the problem is that when we try to ionize our target, the other components are usually ionized as well. The way that we usually ionize a compound is by using an acidic pH to provide proton H positive in the mixture. So they would ionize our samples, our targets. But the point is that when we have other components together with our target compound, the protons that we provide in the sample is used by all of them. And actually, the compounds compete with each other for ionization based on their proton affinity. If we have a compound in the mixture which has higher proton affinity than our compound, then they are going to get ionized, and our compounds are not efficiently ionized. And as I showed you in this slide, we have 4 nanogram of our target compound, and we try to ionize them, but 2 of them get ionized, and the other protons are used by the other component of the mixture. And when you inject such sample to the LCMS, you get a signal which is equivalent to 2 nanogram. That means you made a mistake. the concentration was 4 nanogram, and now we are reporting 2 nanogram of this compound. Why? Because of the matrix effect. We have a matrix in which there are some components which have higher proton affinity than our compound, and they use all the protons in their mixture, and our compound is not totally and completely ionized. And the signal is going to be proportional to the part of the compound which is ionized. And then we will have the wrong answer. We are giving the wrong concentration, which is not acceptable. This is called matrix effect or ion suppression, in other words. And this is the Achilles heel of LCMS. This is one of the largest and one of the main shortcomings of the liquid chromatography mass spectrometry. But we have to think about it, and we have to arrange the system so that we can avoid the matrix effect, and this will not cause wrong answer for us. I'll explain you how we do it. Could we have the next slide, please? This brings us to the other capability of mass spectrometry, which is very unique, and we have no other detector which is so selective, and it has this characteristic. You all know about the isotopes. Isotopes are those atoms which are different from the main atom by the number of the neutrons, and you all know about the deuterium. You all know about which is the isotope of hydrogen, and we all know about carbon-13, which is the isotope of carbon-12. If you look into the nature, if you analyze the carbons that we have in the nature, 99% of the carbons are C12. And 1% of the carbons in the nature are C13. C13 and C12 are both carbon, and they are not different. They have the same physical chemical properties, and they are not different in their chemical behaviors and physical behaviors. They are just different in their atomic weight. And they could be discriminated, and they could be differentiated from each other by mass spectrometry. Next slide, please. Now imagine that we have a compound, one of the biomarkers. For instance, this is phenylalanine. Phenylalanine has a phenyl ring in its structure. And imagine a compound in which we have all the hydrogens of phenyl group replaced by deuterium, which is the isotope of hydrogen. They are both phenylalanine. They both have the same chemical structures, and they both have the chemical behavior and also physical behaviors. Their extractability are the same. Their solubilities are the same, but the only difference that they have is their molecular weight, because phenylalanine has a molecular weight of 165, and when you replace all the hydrogen with the deuterium, then you will have a phenylalanine which has the same physical and chemical properties, but its molecular weight, its weight is different. It's 170, because having 5 deuterium instead of 5 hydrogen will add 5 atomic mass unit to this molecular weight of phenylalanine. Could we have next slide? Now, if we compare these two structures, these two compounds, as I said, they have the same physical properties, they have the same chemical properties, same solubility, same extractability. So these two compounds are not different. They are both phenylalanine. But the only difference, the natural phenylalanine has a molecular weight of 165, and the isotope phenylalanine, the phenylalanine which has all the hydrogen replaced by deuterium, has different molecular weight, which is 170. I have to mention that the first one, the phenylalanine with hydrogen, is the phenylalanine that you find in the nature. But you cannot find a phenylalanine in the nature which has all the hydrogen replaced by deuterium. These are the compounds that we make them in the lab, these are not natural. They are called stable isotope labeled compounds. These are the compounds that we make them by replacing the natural isotopes with their different isotopes, for instance, deuterium instead of hydrogen. And as I said, you cannot find this in the nature. That's why we call them stable isotope labeled compound. They are very expensive to be made, but they are very good tools for mass spectrometry, and they are very good tools to avoid the matrix effect in mass spectrometry. How is it done? See, since these two compounds are identical in physical properties, they have the same solubility, same extractability, same chemical properties. Their behavior in the solution are the same. But when it comes to the mass spectrometry, when you inject both of these together to the mass spectrometer, they will give separate signals, because the first one, the natural one, has different molecular weight from the labeled one. And you get two signals for each one of them. Of course, if you have a chromatographic system, they will elute together, they co-elute at the same time. But since the masses are different and their mass fragmentation are different, the machine is going to get two signals, separate signals from each one of these. How this is used for metabolic disorder screening, I'll explain it in the other slide. Okay, here I have the same picture that I showed you as the ion suppression process that we had in the other slide. See, let's say we have 4 nanogram of the natural phenylalanine, which is the blue dots in here. And let's say I add 2 nanogram of the labeled phenylalanine, which is shown in red in here. And they are all mixed together, and we ionize them, and we inject them to the LCMS system. Well, of course, we get a proportional signal for each one of them. Since I have a 4 nanogram of the natural, which is the blue one, I get the signal for the blue, the natural phenylalanine, and I get another signal for the labeled phenylalanine, which of course, since the concentration is half of the natural, the signal is going to be half of the signal, the natural as well. And you see that a picture in here in which we have a blue signal, which is twice as the red signal. The ratio will be 4:2, which is equal to 2. Now, this is when we don't have the matrix effect, when we don't have any other components of the sample along with our analyte. Now, let's say we have the phenylalanine in blood, and we have the same number as I explained in the above sample. But now we have other components of the blood competing with our analyte, which is phenylalanine, and they have higher proton affinity than phenylalanine. So they use part of the protons that we have in the solution. And the same scenario will happen that I explained in my previous slide. from the 4 nanogram of the natural phenylalanine, just half of them are ionized. That means 2 out of 4 are ionized. Since the label phenylalanine, the red ones, have the same solubility, same proton affinity, same extractability of the phenylalanine, the natural phenylalanine, the same thing is going to happen to the labeled phenylalanine. That means from the 2 phenylalanine, labeled phenylalanine that we have, half of them, that means 1 of them, is going to be ionized. And then when you inject this sample to the LCMS, you get 2 signals, one for the natural phenylalanine, the other one for the labeled phenylalanine. Yes, both signals are smaller than the top scheme, but the ratio is going to be the same, 2 to 1. That means if I have the labeled along with the natural phenylalanine, I could compensate and I could calculate I could compensate for the ion suppression by comparing the intensity of the 2 signals with each other. As you see in here, I have 2 blue, that means the natural phenylalanine, to 1 labeled phenylalanine, and the ratio is going to be to 2. And in the top picture, I have 4 phenylalanine, natural phenylalanine, divided by 2, which is equal again to 2. And both of these numbers are equivalent to 4 nanogram of the sample. So if I have the labeled phenylalanine along with the natural phenylalanine, by comparing the intensity of the 2, I can compensate for ion suppression. How? It is just enough that I know that how much labeled compound I add to the sample. And since the labeled compound is not natural, I mean, the concentration of the labeled compound at the beginning is 0 in the sample. I add a certain amount of the labeled compound at the beginning of the analysis to the sample. And then I go through the extraction processes and through the ionization processes, and then I get a signal. Whatever happened to the natural compound is going to happen, and it's going to be reflected on the labeled compound. And then whatever happens to the labeled compound is going to be happening to the natural compound. This way, we could calculate and we could take into consideration the extraction efficiency, the matrix effect, and this way, by using a certain amount of labeled compound at the very beginning, we could compensate for the losses that we have during the sample preparation processes and during the ionization processes, which is the ion suppression. So this is how we calculate and we take into consideration the matrix effect, which is unavoidable when we are dealing with the blood sample and we extract the samples from the blood. How do we use it for the metabolic disorder screening? I'll explain it in the next slide. See, we have 3 steps when we want to analyze the dry blood spot. As I said, the dry blood spot is taken from the heel of the newborn, the neonate, and it is dried on a filter paper. The filter paper is transferred to the lab, and when it reaches the dry blood spot is in the lab, we make a punch of the size of 3 to 3.2 millimeter in 90 96 well plates. This is a 96 well plate. And as you see, there are in each well, I have one punch of the size of 3.2 of the dry blood spot. After this, we have to go for the extraction. Next slide. So in the next step, we just add enough methanol water at the ratio of 80:2 to the to each well, and we extract the sample for around 20 minutes to 30 minutes by shaking it on a vortex shaker. And all the components of the blood, including those biomarkers, are extracted into methanol. Now we have a methanol which contains all the biomarkers plus all the interfering compounds from the blood. And it is ready to be injected to the mass spectrometer. The third step, which is in next slide, is going to be injecting the methanol solution, methanol extract, to the mass spectrometer. Next slide, please. And as I said, when the sample is injected to the mass spectrometer, we have set up a method in which we have a certain ion monitoring for each one of the biomarkers, as I explained it before. Again, I would like to mention that we have around 50 biomarkers. And for each biomarker, we would like to have a certain ion transition specific for that biomarker. And we would like to monitor them by the mass spectrometer at the same time. The result is going to be a chromatogram in which we have a separate graph, a separate signal for each biomarker. Next slide, please. This is the graph which is generated by mass spectrometer after injecting the sample, the extracted sample to the mass spectrometer. Each one of these graphs that we're looking in this picture is representative of one biomarker. But for each biomarker, we have a label biomarker as well. For instance, if I want to give you an example, we have natural phenylalanine in the dry blood spot. But the methanol solution that we use for extraction contains a certain amount of labeled phenylalanine as well. That goes for all the biomarkers. For instance, one of the other biomarkers that we monitor is methionine. Methionine has a natural, we have natural methionine in the dry blood spot, and we have dissolved a certain amount of methionine in the methanol, which is labeled methionine. Along with our natural methionine, we will have two signals, one for natural methionine and the other one is for labeled methionine. The difference between them is that we know how much methionine, labeled methionine, we have added at the beginning. And that goes for all the biomarkers. We have 13 acylcarnitines and we have 13 amino acids for which we have the label compound for each one of these biomarkers. If I want to explain more, you see that methanol solution, the 80:20 that I explained at the beginning, we dissolve a certain amount of all the biomarkers, all the amino acid, all the 13 amino acids, and all the acylcarnitine to the in the methanol solution. In that methanolic solution, we have the labeled compound at the amount that is calculated very accurately, and we have dissolved them in the methanol. And when you use that methanol solution of the labeled compound for extracting the natural biomarkers, you're getting the natural biomarkers into the methanol solution. And since you have the labeled biomarkers at a certain amount in the same solution, then in this solution, we will have 13 amino acids, natural ones, and 13 labeled amino acids that we have added ourselves. And for the acylcarnitine is the same. We have 13 amino acids. We have 13 acylcarnitines, natural acylcarnitine, which are extracted from the blood spot. And we have added 13 acylcarnitines, which are labeled, and we have added ourselves, and we know the concentration of them. So what we get is 52 graphs. Each graph represents the natural biomarker and its labeled biomarker. And since they have different transitions, we get separate signals for the labeled one and for the natural one. If I have the next slide, I can show it better. See over here, I have extracted the signals which are specific for natural phenylalanine and for the labeled phenylalanine. The natural phenylalanine, which is the blue graph, is extracted from the blood spot. But the labeled phenylalanine, which is shown in red, is the phenylalanine that I have added at the beginning of the extraction myself. And it is added at a very accurate and a certain concentration. So if you see these two graphs and you see the area under the curve for the two graphs, you would say that the natural phenylalanine has the lower concentration than the labeled phenylalanine. So we add the labeled phenylalanine to the sample at the pathological amount. That means we adjust the concentration of labeled phenylalanine at the concentration, which is almost equal to what we have as the pathologic concentration. As I explained before, when we have PKU, the phenylalanine is accumulated in the blood, and it goes higher than a certain amount, which is called pathological border, which is called the pathological concentration. So we add labeled phenylalanine to the dry blood spot at a pathological concentration. And then we extract the dry blood spot by this methanolic solution. The natural phenylalanine is going to be extracted to the methanolic solution, which contains the labeled phenylalanine at the pathological level. And when you inject these, this sample to the mass spectrometer, you get two signals, one for natural phenylalanine and the other one for the labeled phenylalanine. If the labeled phenylalanine is higher and the area under the curve is larger than natural phenylalanine, the phenylalanine is not reached to the pathological level, and this is a healthy baby. But if you have a disorder, if you have a PKU case, you will have the graph the other way around. Just remember, labeled phenylalanine is higher than natural phenylalanine in this slide, which is the healthy baby. Next slide, please. Yeah, over here, I have a PKU case. And as you see, the red graph is labeled phenylalanine, and the blue graph is for natural phenylalanine. This is a case in which the concentration of phenylalanine in blood is very higher than the labeled phenylalanine. As I said before, labeled phenylalanine is added to the sample at a very accurate and certain concentration, which is the pathological concentration. And if the blue graph is higher and it's larger than labeled phenylalanine, it means we have a case of PKU. It means that the concentration of natural phenylalanine has gone higher than pathological amount, which is reflected on the labeled phenylalanine. And having this graph, we could just easily decide that the concentration of natural phenylalanine has gone higher than pathological amount, and this is a PKU case. And this is how we usually, this is how we decide on the result of the test. This goes for all the biomarkers I explained to you. 13 amino acids and 13 acylcarnitines are monitored together during 2 minutes, and the whole process of monitoring takes 2 minutes. And the other aspect of this test that I would like to emphasize and put a stress on it is that since the biomarkers are different in molecular weights, and since each biomarker has its own labeled biomarker, labeled compound, there is no need for separation by column in HPLC. You know, in classic HPLC, we usually use a column to separate the biomarkers, to separate the components of a mixture. But over here, we don't use a column. We just inject the sample, which is extracted by methanol from the dry blood spot, directly to the mass spectrometer. And since all the biomarkers have different molecular weights, and they have their own mass transitions, the mass is going to be able to generate a separate signal for each one of them without being worried about the interferences from the other compounds. So having the column eliminated from HPLC, we will save time because we don't need to wait until all the compounds are separated from each other. Mass spectrometer will separate them based on their difference in mass molecular weights and ion transitions. And we just inject the samples directly to the mass, which is called flow injection analysis, as opposed to column separation, which is used in classical HPLC. So we don't have any column. We just inject the samples after extraction directly to the mass. And since we have separate ion transitions for each biomarker, the instrument is going to discriminate all of them, and we don't have any interferences from the other compounds on the main compounds. So this will give us a very fast analysis. And it will also give us a very comprehensive analysis because we are analyzing all these biomarkers all together at the same time during the 2 minutes of the flow injection analysis. And it is also accurate because each biomarker has its own ion transition, which is different from the ion transition for the other biomarker. And as for the calculation of the concentration, the way that the method is set up, as I explained in this slide, is based on the intensity of the labeled phenylalanine, which has been added to the sample at the pathological level. And just by comparing the intensity of the two signals, the labeled one and the natural one, you can decide if the natural phenylalanine or natural biomarker is higher than the labeled biomarker. And you can decide whether the sample is positive or negative this way. Next slide, please. This is a real sample that I'm going to show you, and I would like to compare the intensity of the signal. This is a normal PKU compared to a pathological PKU. You see the top mass spectrometer, the top mass spectrum is the result of the injection of a normal sample, that means a healthy baby, in which you have two signals, one for natural phenylalanine on your left by the green arrow, and the labeled phenylalanine, it's called D5-phenylalanine because it has 5 deuterium in its structure on your right by green arrow. As you see, the intensity of D5-phenylalanine is larger than natural phenylalanine. That means the phenylalanine, the natural phenylalanine, has not reached the pathological level. But look at the other spectrum in the bottom. As you see in here, again, we have natural phenylalanine on your left, and the labeled phenylalanine are on your right hand. The labeled phenylalanine on your right hand has been added to the sample at the pathological concentration. And as you see in here, labeled the natural phenylalanine is way larger than the labeled phenylalanine. And since the labeled phenylalanine has been added at the pathological concentration to the sample, having the larger signal for a natural phenylalanine shows you a pathological case. And this is a PKU case. Next slide, please. This is another example of a metabolic disorder, which is called MCAD, medium chain fatty acid disorder. And again, we have the normal case here, the healthy baby on top, and we have the pathological case at the bottom. On top, you have a mass spectrum, and as you see, the labeled C8, that means a fatty acid with 8 carbon is attached to the carnitine. We call it C8. The intensity of labeled C8, which is added by ourselves to the sample, is a signal which is shown by the green arrow on top. And as you see, there's almost no signal for natural C8 because they have all been shuttled by carnitine to the mitochondria, and we don't have any C8 in the dry blood spot because this is a normal case. But look at the bottom spectrum. At the bottom spectrum, we have labeled C18, again shown by the green arrow, which is pretty small. But the difference is that in this case, we have a very large signal for C8, for natural C8 carnitine, which is shown by the arrow, the red arrow, and it is almost 10 times of the labeled one. And that means it has exceeded the pathological concentration, and this is a positive case for MCAD, which is one of the very dangerous metabolic disorders. The last example would be on next slide. This is a case which is called isovaleric acidemia, which is one of the acylcarnitine metabolic disorders. And I'm going to, again, show you the normal case and the pathological case. The top mass spectrum is showing the labeled C5 and the natural C5. I'm sorry, the tags are having a mistake. The red one is the natural C5, and the green one is the labeled C5. On top, you see the two signals are almost nothing. I mean, they have concentrations which are not pathologic, and the C5, the natural C5 is smaller than the labeled pathological concentration that I showed you on top. But in the bottom one, we have a case in which C5 carnitine, which is the natural, again, the label is wrong by mistake. The red arrow is showing the C5 carnitine, natural C5 carnitine in the blood spot, and the green arrow in the bottom is showing the labeled C5. And as you see, the intensity of the signal for natural C5 carnitine has exceeded the pathological concentration. And that means we are having a isovaleric acidemia pathological case. And this is a baby that should be referred as the positive isovaleric acidemia. If I want to just wrap up my talk, as you see, we use mass spectrometry in metabolic disorder screening for accurate determination of the pathological cases. And what we use in here is selected ion monitoring for the accuracy and selectivity of the test. And we use flow injection analysis. That means we don't use any column to separate the biomarkers. The separation of the biomarkers are based on their differences in their molecular weight. And that means the mass spectrometer is going to separate them and discriminate them from each other. And the main point is that we extract the dry blood spot with a methanol water solution, which contains the labeled biomarkers. The labeled biomarkers are used at the concentration, which is called pathological concentration. And when we extract this dry blood spot with this methanol, which contains the labeled biomarkers, we will have the natural biomarkers extracted to the methanol. And when you inject these samples to the mass spectrometer, you get two signals for each biomarker, one for natural, the other one for labeled one. If the natural signal is more intense than the labeled one, you will have a pathological case. And if the natural signal is smaller and it's lower than the labeled biomarker, then we will have a normal case. And that's the whole idea of analyzing metabolic disorder using the capacities and capabilities of mass spectrometry. With that, I would end my talk, and I will thank everyone for paying attention. I hope I was able to get across the method. Of course, I could explain more and go on and on, but we don't have time. And I will try to show you the process in the lab when we have the demonstration of this method. Thank you so much for your attention. And with that, I will end my talk and wait for the organizers to tell me what to do next. Thank you so much.
Thank you very much, Professor Dr. Farzad. It was an excellent and a very comprehensive presentation indeed. So we have some questions in the chat box, but I would, since we have only 20 minutes left for this session, so would you recommend that we go for the virtual lab tour first, and then we can take question answers at the end? Is that okay to you?
Sure, definitely. Just give me 2-3 minutes to go to the lab, and I will connect again, and we could have the rest of our presentation in the lab.
Sure, thank you.
Thank you. Dr. Khazima?
Yes, Dr. Farzad. Yes, we
Do you
can
have
see
my
you.
voice?
Yes.
Okay. Okay. Dr. Khazima, do you have the video as well?
Yes.
Okay. Can I go on?
Yes, sure.
Okay. Here we are in the metabolic disorder screening lab. And I would like to explain a little bit about the process of getting the samples and how the samples are registered, and then how the samples are prepared. And then at the end, when we inject it to the machine and we get the signals. So the samples are going to be transferred to the lab like this. And as I see in here, we have a card which contains the dry blood spot. This is the dry blood spot that we have. And as you see in here, these are this is the filter paper, which has been used in the sampling center. And the dry blood spot has been put on the filter paper. It is dried in the sampling center, and along with the card, which has the information about the baby, the sample is transferred to the lab. After the sample is transferred to the lab, the sample has to be registered first on the computer, and the sample is given a code, a 24-digit code, which contains the information about the age of the baby, the sampling date, the analysis date, and the operator who is going to analyze the sample. After that, the samples are going to be punched in the lab. This is the punching machine. As you see, the 96 well plate is placed in the machine, and then according to a program, the machine is ready for punching, and here is the process of punching. Sonia, who is in charge of the punching, is going to place the filter paper in the machine, and by pressing, we get the punch. As you see, a punch of the size of 3.2 millimeter is taken for that sample. This is the second sample, and you get the punch, as you see in here. I'm going to show you another sample. And this is the punch for this sample. And let's take a look at the 96 well plate, which contains the three spots, the three punches that we had in here, over here. So these are the dry punch that has to be extracted by methanol. So here, Mahsa is adding the, as I said, the methanol water extraction solution. The extraction solution contains all the labeled compound, the 13 amino acid labeled compound and 13 acylcarnitines. So the solution is added to the well plates at a certain amount. And as I explained in my lecture, this solution contains all the labeled compounds at a certain and accurate concentration, which are equivalent to the pathological concentrations. So after the solution is added, the plate will go to the shaking machine, a vortex shaker, basically.
And it is shaken for around 25, 30 minutes, and all the components of the blood, including the biomarkers that we talked about, are extracted into the methanolic solution. As I mentioned before, the methanolic solution contains all the labeled compounds, 13 amino acid labeled compound and 13 acylcarnitines. And now we are extracting the natural biomarkers, 13 amino acids natural and 13 natural labeled compounds of the natural acylcarnitines are being extracted to the methanol. And after the process is done, after the extraction is complete, the sample is ready for being injected to the machine. And you have to mention that there are two different methods of sample preparation. One is called non-derivatized method, which is being shown in here. There is another method which is called derivatized the derivatized method. In that method, we usually make it we will go through a process of derivatization reaction, which is going to take more time. But if you are a lab which is getting many samples a day, you would prefer to go with the non-derivatized method, which is the method that I'm showing you. It is just a matter of extracting all the biomarkers in methanol. And then after the extraction process is finished, the sample goes directly to the machine, to the CMS machine, and you will have the analysis in 2 minutes. So Marjan is going to take the sample after the extraction from the shaking machine, and the samples. The methanol solution, which is containing all the biomarkers, are going to be transferred to another well plate. This is just to separate the punch, the filter paper from the extraction solution. Now we have the extraction solution ready for the injection to the machine. At the end of this process, we have the samples ready to be injected. And as you see in here, the samples are placed into the auto sampler of the machine. And with the sequence which has been written before, we can start injecting the samples to the machine. And after the injection, we'll get the signals. I'm going to show you the generation of the signal as it goes. And you will see all the graphs as I've shown you before. It takes just a few seconds. This is the previous graph that we had for the previous sample, but the machine is injecting the sample to the mass spectrometer. And as you see in here, the auto sample is taking the sample. And it's going to inject the sample into the machine. Well, the sample is injected now, and we can see the graph which is being generated by the machine. And these are the graphs which are being generated by the machine. And as you see in here, each graph represents one of the biomarkers. And for each biomarker, we have two signals, one for natural biomarker and the other one for the labeled one. And the total ion chromatogram, which is being generated now, contains all the information about all the biomarkers. And I want to show you the selectivity of the mass by extracting for one of the biomarkers. Majan is going to extract phenylalanine and the labeled phenylalanine, and you will see the two graphs in here. The red one is the labeled phenylalanine, and the blue graph is the natural phenylalanine. And as you see, the intensity of the signal, the blue signal, which is for natural, is lower than the signal for the labeled phenylalanine. And that means we are having a healthy baby, and the amount of phenylalanine has not exceeded the pathological border. And this is a healthy baby. And if we had a pathological case, the intensity of the two signals would be the other way around and opposite of this that we have in here. So this is the whole process of metabolic disorder screening. I hope I was able to show you the whole process. I just want to mention that when you have around 200, 300 samples a day, then this process, will have to be run during the night and 24 hours a day. For each sample, it takes 2.5 minutes to be analyzed. And after the analysis is done, we use a software to process the data automatically and generate all the numbers and all the concentrations based on the intensity and the area under the curve for each biomarker. I'm not sure if you will be able to see this, but this is the kind of report that we get for all the biomarkers. Since we have many samples a day, for instance, 300 samples a day, then looking at each sample one by an operator is pretty difficult. So we have a software which is used for processing the data. That means it calculates all the area under the curve for the biomarkers and the labels. It compared them. It uses an equation to calculate the concentration, and it gives us the concentration of each biomarker. And then it compares the concentration of each biomarker with the labeled biomarker. And if the concentration of the natural biomarker has exceeded the intensity of the labeled biomarker, then it would give us a warning as too high concentration. And by looking at the report, we'll be able to pick up the pathological cases, which is shown in here. What we have here is one of the reports. And as you see in this report, the biomarker of phenylalanine has been more than the pathological level, and it says too high, and it gives us a warning. For the other biomarkers, all the concentration has passed, and we have no abnormal concentration of the other biomarkers. So this is a PKU case, which is reported to the health center, and the baby is recalled, and the proper action would be taken by the medical team for this baby. So I'm gonna go around the lab. As you see, all the equipment which are needed, the reception for registration, the sample preparation lab in which we have the extraction process. And finally, after the extraction is done, we'll go to the analysis lab, which is the mass spectrometry lab. I hope I was able to show you around, and if there is any questions, I'll be happy to answer those.
Thank you very much, Dr. Farzad. It was, I must say it was the most amazing part of the whole 2-hour session today. And I would like to thank you as well as your team for their time and, for letting us be part of their work life for 2 hours as well. And Dr. Farzad, if you allow me, we have some questions in the chat box. So I'll read them out for you.
Hazima, in the meanwhile, I can also ask 1 or 2 questions if allows.
Yes, sir. Sure. I think you should go ahead and ask questions first, please.
Fine. Brother Farzad, I mean, indeed a very wonderful presentation, very informative lecture as well as the visit as well. So congratulations for that first. I have a couple of questions. Number one, that you have mentioned that you are not using the LC and you are just, the flow injection mass pack, which is indeed a very rapid technique. So how often do you clean the ion source? Because the direct injection, a continuous direct injection may cause a serious contamination. So this is my first question. The second question is as you have entered the deuterated standards and the methanol in the extracting solvent. So does it really provide a true picture of matrix effect? Because usually in analytical sample preparation, we allow the internal standards to get first absorbed in the matrix, then re-extract it. So how often do you feel that it really provides, I mean, is that okay, for the extraction like this way? And third one, that what about the transportation and storage condition of the dried blood spot? Is that really okay to just transport at room temperature and, the analysis, or is there any timeline or storage condition for the storage transportation analysis? Thank you very much.
Okay. Well, thank you so much for a very excellent question. And first, thank you for the nice remark that you made. And the very, very good question, Dr. Mashara. As far as the cleaning of the system, yes, it depends on how many samples you get during the day. And our lab is getting around 250 to 300 samples a day. So that's a very large load of samples a day. And we clean up the samples each week, every week. Of course, since this was paper, you have these particles coming out of the filter paper, and they might block the path of the solvents in the system, in the LC system. They do get clogged sometimes, and we need to constantly monitor the pressure of the HPLC pump and see if there is a change in those. And if there is a change in the pressure, we will realize that we have a blockage. We have to stop the machine, clean up the machine, and then start over. But if I just want to give you an average, having 200 samples a day, we usually have our cleaning every day, every week, every 7 days. And then we will have no problem, unless we have abnormal pressure, and that means something has happened to the system, and we have to act accordingly. The second question, could you say again what was the second question?
Internal standard
okay.
used in a
Yeah,
solution. Yeah.
yes. I recall. You were pointing out a very good point about the extraction. See, the extraction solvent contains all the labeled compound, and it is not that we add the labeled compound to the dry blood spot and then mix them and then we extract them. But the point is that the extraction time so that we could get all the biomarkers out of the dry blood spot. And that is half an hour shaking. Half an hour is going to be enough to get all the biomarkers out of the dry blood spot, which, as I said, it's the size of a 3.2 millimeter punch. And in order to make sure that the process has been done properly and we have not missed anything, we have control sample. And in each 96 well plate, we get analyze 2 control samples. These control samples are dry blood spots in which the concentration of all the biomarkers are determined before, and we have a table of the concentration for them. So we include the 2 control samples for each 96 well plates, and we control our performance based on the result that we get control sample. This is one of the requirements of the analysis. Otherwise, we cannot make sure that we are doing the right. We are conducting the test. When we get the samples out of the machine and we analyze them, the first thing that we look is the result of the control sample and comparing them with the target concentrations. If we have hit the target concentrations, then everything has been fine. But if there is some problem, for instance, all the values are lower than what it has to be, then we will realize that we have had some problem with the extraction process, and we repeat the process. But this doesn't happen that often. As I said, we have optimized the extraction process. The ratio of 80 to 20, 80 metal, 20 part water is the proper and suitable concentration of the extraction solution. And 1 hour would be enough to get all of the markers out of the dry blood. And this way, we will have no problem with the extraction process. And as I said, we control them. We controlled ourselves by analyzing the control sample. And we make sure that all the processes are done properly. The third question that you had was about the storage of the DBS or dry blood spot. You know, one of the advantages of this process and one of the requirements of this process is the nature of the sample. As you see, the nature of the sample is a whole blood, which is dried on a piece of filter paper. The test has been set up this way so that the sampling process is easy, and also the transfer of the sample and the storage condition of the sample is pretty simple. This could be kept at room temperature for a long time, I would say 6 months, and no changes made in the biomarkers because the sample is dry. You know, if you have a plasma sample or if you have blood sample frozen in the freezer, they start degrading. But since the sample is dry in here and it's on the filter paper and a piece of filter paper, it will allow us to have a normal condition for their storage. There is no specific condition for keeping them, and the samples are stable for a long period of time. Of course, in the lab, when we get abnormal samples, we keep them in the freezer, just in case. We don't want to, because the positive samples are precious and very important for the lab. We keep them in the freezer at the minus 20 degrees C, but there is no need for storage of the samples in specific conditions. We do recommend all the sampling centers to transfer the samples in a cool box. That means with an ice pack. But it is not necessary, actually. And the samples could be just put in an envelope, just like a letter, and sent to the lab as soon as they are collected.
Thank you very much, Brother Farzad.
Sure, definitely.
Thank you very much, Dr. Farzad. So we have some questions in the chat box. First one is from Mr. Shajat Ali. He's asking, is there any in situ test for PKU?
Any what test?
In situ test for PKU.
Could you elaborate more? What do you mean by in vitro test?
Okay, I'll ask.
Those are, you mean before the birth, right?
Yes.
Yeah, see, the test that we are doing is called after delivery test. And there are some tests, some genetic tests, which could be conducted before the baby is born. We are not involved in those tests. I mean, those are NGS, and actually, they need different type of machines and different type of sample preparation and systems. What we are doing is screening after the baby is born. This system is not used for before delivery. We are just involved in the after delivery test and the screening.
Okay, so here is another question from Mr. John Bonda. He's asking, is it possible to extend this diagnostic technology to adults and save lives?
I didn't get the last part. Is it possible to send the test to what?
To use this diagnostic technology for the adults.
For the adults, yes, yes, it's possible. Yes, actually, it's definitely possible. But there is just one point that I have to mention. See, for each biomarker, for each of the amino acids and acylcarnitines that I mentioned in my lecture, there is a cutoff. There is a certain amount that higher than amount is considered as pathological, and there's a certain amount which is called normal, and the sample is considered healthy. The cutoff for the babies are different from adults. You know, adults eat everything, and they are in their own diet and the type of the food that they get, and all of them are going to affect the concentration of these biomarkers. So the cutoff are different for the adults, but yes, if someone is having a metabolic disorder for any reason, it could be congenital or incongenital. But the point is that the congenital disorders has to be diagnosed at the very first days of the birth. And they usually are precious if they are done during the golden time of the first days of the birth. And as I said, if they are neglected and if they are missed, then they will have their consequences. But if someone is affected by some other parameters and there are disorders due to other parameters, except for the congenitals, we will be able to measure the amount of all the biomarkers for their blood as well. But the point is that the physician or the diagnosis team has to be familiar with the cutoffs for the adults. And as I said, since adults have different food consumptions and they use different foods, the amount is going to be very different among them. But for the babies, there are cutoffs which are set up for each population. And what we are supposed to do is comparing the amounts with the pathological cutoff for the babies, for the newborns. And we cannot, if I want to give an example, if a baby is born immaturely, if a baby is immature, the cutoff is different. If the baby is, for instance, 2-year-old, the cutoff is different. What we have in our lab, and we compare the amount of the biomarkers with that amount, is the cutoff for the newborns.
Okay, so here is a last question. So Ms. Samia wanted to know, what is the cost of this test?
Oh, okay. The cost of the test, if you get sporadic samples, that means if you get 2-3 samples a day, the cost is very high because you have to set up the whole system for 2-3 samples a day. I mean, the mass spectrometer is pretty expensive, as you know. The label, the standard that I mentioned, and I said that they are made synthetically by suppliers, by specific suppliers like Cambridge Isotopes and Chrome System or Perkin Elmer. They are pretty expensive. But if you get many samples a day, the costs are going to be divided. And if I want to give you a correct number, I would say if you have enough samples a day, the cost for each sample, as we have calculated before in our lab, is going to be $2.5 US, considering the price of the labeled compound, the LCMS machine and extraction solutions, the well plates, the pipette tips, the punchers, everything. It's around $2.5 US for each sample.
Thank you very much, Dr. Farzad. With this, we come to the end of our session. I would again like to thank you for your time. It was wonderful having you, and we hope to see you sometime in Pakistan as well, especially in Comstech, Islamabad. And I would also like to thank our participants who remained with us throughout this session and were a very good audience, I must say. And this lecture is recorded and will be available on Comstech's YouTube channel. And in addition to that, I would also like to say that all the participants will receive their e-certificates within 10 working days of this after this lecture. So thank you very much. And with this, again, thank you and bye-bye. Hope to see you in another.
I would like to thank you and Dr. Musharraf, and my special thanks to Dr. Iqbal for arranging this event. And I hope I could get the message across. And if not, I will be available and everybody invited to email me and ask me questions regarding the whole processes. It was a pleasure being part of this event, and I hope the best for everyone. Thank you.
Thank you very much, sir. And I would also again like to thank Dr. Musharraf as well for his time and for being very kind to be part of this event today. Thank you very much and bye-bye.
Sure. Bye.